Okay. Let's get started here.
No.
Now, listen. Remember, the whole point is we do a little harder work on the front end for some more relaxation on the back end. I don't know exactly.
40, 20.
I mean, yeah, I don't know. How does number of questions help you study?
Because I know how much to study for.
Yeah, but I mean, I could have 100 one-point questions, or I could have 25 five-point questions. What's the difference? All right. So, we're going to go kind of chapter by chapter here through the study guides. We're going to try to indicate what is important to study and what things you can kind of ignore and not worry about the more fringe things. Hey, listen. I'm trying to help you guys. I could just say, test next Friday, good luck. So, if you don't want the help, you are more than welcome to go sit out in the commons. I have no problem with that. All right. Go for it. On the first page, okay, now I'll kind of explain my notation here. I'm going to go through, I'm going to circle the ones that you need to kind of focus on. Obviously, if I don't circle it, then, you know, it's not a big deal. I may put an arrow next to a couple, and that means you don't need to, like, absolutely know how to do that for a specific problem, but it's an important part of the whole understanding, and hopefully you'll kind of see that as we go. Okay, so here I would go through and I would circle 1, 2, 4, 7, 9, and 10, and then I'll do it when we get down there, 13. I can't quite fit everything on here. Okay. Then I want to go through and talk about those. So let me scoot down so I don't forget. We'll circle 13 down here. No, sorry. Of course, if I don't put graduated cylinder, beaker, or Erlenmeyer flask, it'd be screwed anyway. So, number 1. I know how to pipette, all right. Number 1 says you should be able to indicate the number of significant figures in a measurement, okay? So, and actually, I'm going to put a check mark next to this to show that anything with a check mark over here means I guarantee there will be a specific problem on that. So here, okay, I guarantee there will be a problem where you have a number like this and you're asked how many significant figures are in this number. So here's a decimal right here. So remember, zeros only count if they are trapped in between two numbers or if they're to the far right of the decimal. So if we put a 0 over here too, there's no reason to write this 0 except to show that it should count in your calculations. So here, these zeros wouldn't matter. All they are is placeholders. The 4, obviously not being 0 matters. This 0 matters because of the rule. If it's to the far right of the decimal, it matters. And this 0 matters because it's trapped in between. So this would have 4 significant figures right here. Okay, as another example, we could do something like this. Okay, in this number, these zeros, the whole point is we don't want to count zeros that are just placeholders. All these zeros are here are placeholders. They don't tell you anything about the preciseness of the measurement. And so they don't count. This 0 counts because it's in between. And so we have 1, 2, 3, 4, 5 significant figures there. Now, there's no decimal. Now, let's say I threw a decimal in there, right? If we put a decimal right here, then we would have a 0 to the far right of the decimal, so it would count, and then these zeros would be trapped between significant figures, so that would make all of them count. Okay, so I guarantee you will have a problem like that on the test, and you can look at your tests, old worksheets, to see, and guys realize on the website, I know none of you use the website, but it is there as a resource. It has everything that we've done all the way back. You can find any worksheet on there. You can go back and find the worksheets all for Chapter 1 there if you want to go back and practice some of this stuff if you don't remember how to do it very well. Okay, it goes all the way back to the very first day in here. All right, number 2, you should be able to explain why measurements have significant figures. Remember, the whole point is it comes down to your measuring tool. If your measuring tools were perfect, then there would be no such thing as significant figures. But the point is, if I use this tape measure, I can only really estimate how long something is to a certain preciseness. I mean, I can measure this right here, and I can go, okay, it's 29, but it's not exactly 29. Okay? And the best I can do with this measuring tape is to say 29 and a 16th. Obviously, we'd want to use the metric system. But the point is, I can't go any more precise than that with this thing because, I mean, there's a certain amount of uncertainty built in. If I had a laser set up here, I would have a much more precise number. But the laser would even have some uncertainty, the laser measuring thing. So all tools have uncertainty, and that's why measurements have significant figures. So it comes from uncertainty of measurement tools. The reason why we use the burets in there instead of just dumping some out of a graduated cylinder is the burets are much more precise. There's less uncertainty in your measurements there. Okay, number 4 says you should be able to complete conversions using dimensional analysis. Now, through stoichiometry and stuff, hopefully this has gotten fairly ingrained in you, but for Chapter 1, we had some specific, just problems you had to do. I can pretty much guarantee that I'm going to throw one on there that probably has to do with time because then we don't have to worry about remembering conversions because all of you should know the conversions. So if I asked for you to show me through dimensional analysis how many seconds in 5 years, okay, the commons, you start with the measurement that you're given, right? You have to start with the 5 years, and then we need to put in our measurements so that they cancel. So the easiest thing is to go from years to days. And of course, there's 365 days in a year. And that'll cancel those out, and then we can go from days to hours, and from hours to seconds, because we know there's 3,600 seconds in an hour, 24 hours in a day. Okay? Now, you could do one more thing here and go from hours to minutes and minutes to seconds if you would like. It just depends on if you know the conversions or not. But the whole point is you are canceling out units so that you're left with what you need on the top. Okay? And for the problem that I will have you do on the test, you will have to show the actual dimensional analysis there. Anywhere else on the test where we would normally use dimensional analysis like stoichiometry, I don't care if you show it or not. As long as you do the stoichiometry right, you don't have to show me that you know how to do dimensional analysis. But on this, from this first section, I will ask you to show me the dimensional analysis for something. Okay, number 7 says you should be able to distinguish between the different states of matter. Basically, really all you need to know there is solids, liquids, and gases, and what the molecules are doing. So remember, in a solid, the molecules are locked in place and vibrating. In a liquid, they can exchange positions. And in a gas, they're as far apart from each other as possible. In a solid, they're locked in place and vibrating. In a liquid, they're clumped together, but they can change positions. And in a gas, they are as far apart from each other as possible. Liquids, they're clumped together, but they can exchange positions.
Do you shake water up as they get warmer?
Yes. Yep. I mean, not a lot, but yes. In fact, Pascal was the first one to show that. He made a thing where he hooked a weight on a little paddle that he stuck in water and isolated the system, and he showed that by dropping the weight would drop and turn the paddle, the liquid would heat up. And doing the calculations, he showed how much energy was put in by doing mechanical work on the water. So yes, mixing water up does make it slightly warmer. It's just water can hold a lot of energy, so you have to really mix it a lot and fast for it to gain enough energy that you would notice.
Are we going to have to know plasma?
No. Focus on solid, liquid, and gas. Okay, number 9 says you should be able to explain the point of absolute zero and the Kelvin temperature scale. Well, you can't actually get to absolute zero, right? But the point of absolute zero, remember, is that's theoretically where molecules would stop moving. So theoretically, if you could get a system to absolute zero, all the molecules should stop moving. And the point of the Kelvin temperature scale is just to have not have negative temperatures. Because remember, temperature should describe how fast the molecules are moving. So it's kind of weird to have a negative temperature if it's molecular movement. So really the whole point is just to start the temperature of the Kelvin temperature scale is to start the scale where molecules start moving.
Theoretically, if you were to freeze a cell at absolute zero, would it die? Or would it
Way before that, because ice would form and everything would crystallize. And because ice expands, it would basically blow everything up. Okay. Number 10 says you should be able to complete concentration calculations. Here, and this is a little bit out of place, honestly, because we didn't talk about moles till later, but the concentration calculations that I want you to be able to do is for molarity. Okay, and this is another one where I guarantee there will be something on the test. Just going to put a check mark there. Moles over liters, yeah. So a basic problem would be like you have 5 grams of lithium hydroxide and you put it in a liter of water, what would be the concentration? So you got to figure out how many moles there are and then just divide that by how many liters you're dissolving it into. Okay, and then number 13, you should be able to differentiate between the different types of substances and mixtures. Really, we're focusing on substances here. We'll forget about the mixtures. So the main substances, or the 2 substances, remember, are elements and compounds. Elements are made of one kind of atom. Compounds are made of 2 or more atoms in a chemical bond. Basically, if you can find it on the periodic table, it's an element. If you can't, then it's got to be a compound.
Yeah, what kind of bond is it?
Chemical bond. So aluminum, carbon, nitrogen, oxygen, all of those are elements.
we're not focusing on mixtures?
No. Sodium hydroxide would be a compound. Water is a compound because it's made of oxygen and hydrogen.
Why isn't water
Diprotic acid. Because remember, hydroxide, OH, the bonds there, basically it's not going to be able to ionize the O and the H apart from each other. So once water loses a hydrogen, then all you have left is a hydroxide, and that can't be pulled apart.
But in that form, wouldn't it be in the H2O form?
I mean, like I said, it looks like it, right, from the outset, but for it to actually be a diprotic acid, each of those hydrogens have to come off. That's why there's some other things that you'll find on there where there's more hydrogens in the actual formula, but those don't count as far as the acid because they won't disassociate. All right, and then I would put an arrow right here, indicate the correct order of metric prefixes from nano to giga. Really, I mean, we need to know milli to base to kilo. Okay, and remember, those are relationships of 1,000. There's 1,000 milliliters in a liter, right? There's 1,000 meters in a kilometer. So each of those is a jump of 1,000. And I'm not going to, and the reason why we have an arrow there, I'm not going to ask you a specific question about that, but you will see places where you need to convert, and we know that from doing the acid stuff, we need to convert between milliliters and liters. So that's something good to know. So the arrows just indicate stuff that it's good to know, but there won't be specific questions about. Okay, any questions on Chapter 1?
So to get from base to kilo, you would divide by 1,000? Like if you have...
Yeah, you would divide. So if you're moving up here, you would divide. If you have milliliters and you need to put it into liters, you would divide. If you have the liters and you need to go to milliliters, you would multiply. All right, on to Chapter 2. In Chapter 2, we studied the structure of the atom, and we talked about moles. Okay. This is a case where all the stuff we talked about is pretty fundamental, so I would circle everything except number 6. Which seems like a lot, but as you'll see, some of this stuff is pretty basic and simple. So, for example, number 1, describe the overall structure of an atom, including the location of the protons, neutrons, and electrons, and the empty space in between. I mean, it really almost describes it right there. Protons and neutrons are in the nucleus. Electrons are in the orbitals around the outside. And there's nothing in between. Remember, nothing, or empty space does not mean air. These things are smaller than air. Air is made up of atoms. So that's really all you need to know there. Protons and neutrons are found in the nucleus. Electrons are in the orbitals in the electron cloud. What? Yeah, it's nothingness. Vacuum. It's completely empty. There's nothing there.
Like, you can't even...
It's hard to even think about. But
How do you know?
because things have to be made of atoms, and they're smaller than atoms, so what would be in there? Possibly, but there's really nothing that makes sense there. Okay, number 2, also fairly simple. Compare the relative sizes and charges of protons, neutrons, and electrons. So what's the charge of a proton? Positive. Neutron?
Neutral.
And electron? Okay, so we should have that down. Remember that protons and neutrons are about the same size. A neutron is slightly more massive, but we can just remember that they're about the same size. Protons and neutrons are about the same size. Okay? So, and then the electron is 1,000 times smaller than either of those. Now, you don't necessarily need to remember which one is bigger, But I would like you to understand that they're not exactly the same size, but they're roughly the same size. Okay. So just make sure you don't indicate that they are exactly the same size.
Neutrons are slightly bigger?
Neutrons are slightly more massive. Yes. Volume doesn't make a lot of sense at that scale, so we look at mass. Okay, number 3, be able to identify an element based on the number of protons in the nucleus and vice versa. You can put a check mark next to this. I guarantee I will give you a problem on this. But this is fairly simple. If I say, hey, this element has 56 protons in it.
Hold on, let me get it. BA. Oh,
I don't even see. Oh, yeah, right there. Barium. Okay? Or if I say, how many protons are in silver? So we find silver, Ag. Don't get worried. Remember, your periodic tables have the names on there too. So it's got 47 protons. That should be pretty simple.
For final, we should have to memorize the
That would be dumb. That would be a waste of time.
really hard.
Okay, number 4 says you should be able to identify the mass of an isotope by the number of protons and neutrons in the nucleus and vice versa. So this is kind of related to number 3. But if I said we had something that had 14 protons and 16 neutrons, first of all, what element would that be? Yeah, silicon. Okay. And what would the mass be?
28.09 grams.
That's the average mass. Okay. Remember, those on there are average molar masses. But if we're talking about a specific atom that has exactly 14 protons and 16 neutrons, what is the mass of that actual atom?
60. Oh, atom together.
Atom together. 30. 30 AMU, or atomic mass units. So remember, to find the mass of a specific atom, you just add the protons and neutrons together. Now, how that relates to these, remember, is these are averages. If you average all of the atoms in a natural sample, so I can't think of a word, common sample, I don't know. If you take a normal sample of silicon and you average all the atoms together, then their average mass would be 28.09. So that would tell us not very many atoms would have a mass of 30. That'd be fairly uncommon, but this is an average of trillions and trillions of atoms, remember, okay? And we do that because we can relate it to the molar mass then.
How do you find the averages of those ones on the bottom if they're not natural?
Because these are specifically made in particle accelerators by smashing two things together, and we know the masses of the two things that get smashed together. And there's other ways to tell too, but okay, now number 5 says be able to use both of the isotopic notations to show the specific isotope of an element. Okay? Remember, the whole point of an isotope, a specific isotope, is we're talking about a specific atom with a specific mass, and that's what we have right here. There's 2 ways that you would write down what this element is with their isotopic notation. The simple way is just to write the name, so silicon, and then put a dash and put the weight. So silicon 30 would be that specific isotope. So this is one of the ways. Okay? In the other way, we use the symbol. Well, not exactly, and you got it back and upside down too. 30 on top and 14 on the bottom. We put the mass on top and the number of protons. And the reason why I guess I don't know that this is necessarily the reason why we can do it, but it makes it easy then to find the number of neutrons because we can just take the mass and subtract the number of protons. Because remember, the protons do not change in silicon. So this would be the isotope of silicon that we were talking about here. This would be a different isotope of silicon. And we see they both have the same number of protons, but we could subtract to find how many neutrons. And hopefully we can see from this has 2 more neutrons. It's a little bit heavier. Okay? So this is another one here. I would guarantee I will have a problem on there where I give you a number of protons and a number of neutrons and ask you to give me the isotopic symbols. And I will ask for both. So make sure you know how to do both of them. That was just another one that I came up with, just to show the difference. So the only difference between these silicon atoms, remember, is the weight because there's a different number of neutrons. Okay, the protons cannot change. Yes, I will ask for both isotopic symbols. So the question, I mean, I don't know which one I'll pick, obviously, but the question would be something like an atom has 8 protons and 9 neutrons. Write both isotopic symbols for that. And so if it has 8 protons, it's got to be oxygen. So you would add 8 and 9 together, get 17, so it would be oxygen 17, or you'd have the O with the 17 on top and the 8 on the bottom. Okay, and then number 7 should be pretty obvious. I sure hope you're joking. Converting between number of atoms, moles, and grams. Now, moles and grams, we've done so many times, right? You use the molar mass. For Avogadro's constant, you're going between atoms and moles. Okay? It'd be a good idea to look at the mole roadmap, and I guess maybe I can try to get that out for Monday. But remember, the mole is the thing that hooks everything together, right? To go between moles and grams, I should have a double-sided arrow here, you use the molar mass. To go between moles and number of atoms, you use 6.02 times 10 to the 23rd, Avogadro's number. And I will get the roadmap set up so we can look at it for Monday, because in the next chapter we'll have to talk about adding in, converting between liters of a gas as well. Okay, and dimensional analysis here is your friend. Remember, molar mass is in grams per mole. That's the unit. And you should not forget that because I wrote it right up here. You can always look up here if you get confused. Grams per 1 mole. All of these are in grams per 1 mole. 30.97 grams for every 1 mole. 20.18 grams for every 1 mole. Okay? Remember this right here. This is in atoms per mole. And all of these, the whole point of the mole roadmap is to show that all of these are related to moles. Moles is the thing that connects everything. Okay? So this is how many atoms there are in a mole of something. This is how many grams. Remember, this is the same for any substance. Right? Doesn't matter if we're talking about boron or carbon or oxygen. There's always this many atoms per mole. This is going to be dependent on which thing that you're talking about. And if it's a compound, you have to put all of the molar masses together. Okay, any questions there? All right, chapter 3. We're not going to get all the way through it, but we're going to start it. All right, for chapter 3, we studied electrons and how they behave in atoms.
Are you sure we did chapter 3?
Pretty sure. This is where we learned how to do electron configurations and that kind of stuff.
Number 1 doesn't ring a bell.
All right, listen. I'm going to explain. I would circle 3, 4, 5, and 6. Okay, now, we're going to throw some arrows there because even though you might not remember these things by name, they are important for understanding how electrons go into orbitals. Remember, really all you need to know from this stuff is that electrons are going to fill the lowest energy level first. Right? No two electrons can be the same, so they either have to be in different orbitals or different energy levels or whatever. And then for number two, it is also good to know that electrons are not little marbles. They're not little things. They're kind of this diffuse, weird wave-like thing, but we can model them in a way with orbitals that at least makes it make sense as far as chemistry goes. I just want you to make sure you know that electrons are not little particles, not little things that you can grab on a hold of. We don't really understand their physicality all that well, or can't describe it in words as well as we can with math. Not really, no. All right, number 3. Let's do that one, then we'll be done. Recognize the relative shapes of each of the different kinds of orbitals. So remember, there are s orbitals, there are p orbitals, there are d orbitals, and there are f orbitals. And as far as the shapes go, the biggest thing to remember is they get more complex as you go, right? S orbitals are just a sphere. P orbitals have 3 things coming off. D orbitals have 5 things coming off. F orbitals have 7 things coming off. So if you remember, look at your test for Chapter 3 on the back. You should just be able to pick from a bunch of different shapes, which are S, P, D, and F. No, I think that one, almost everybody got that one right. All right, we will continue with this on Monday. Have a good weekend.
One try.